Hello everyone, welcome to my channel. In this lecture, we will discuss about the multiple reaction. So, in the previous lectures, we have discussed about the single reaction. For example, A is converting into B. So, this is a single reaction. In this lecture, we will discuss about the multiple reaction. For example, A is converting into B, but A is also converting into C. So, this is a multiple reaction. One reaction is this one. This is one reaction and this is the second reaction. So similarly, suppose A is converting into B, B is converting into C, C is converting into D. So this is multiple reactions. In this lecture, we will discuss about multiple reaction. So sometimes we have more than one reaction and we want to increase the concentration of one product or some product. Similarly, sometimes we want to decrease the concentration of another product. So we want to desire product. We want to increase the concentration of desired product and we do not want to increase the concentration of desired product. So we don't need undesirable product. We want to decrease the concentration of undesirable product. So we can increase the concentration of desired product and we can also decrease the concentration of undesirable product. Undesirable product are those product which we don't want and desirable product are those which we want to increase their concentration. So there are many type of reaction. There are many type of multiple reaction. One is the parallel reaction, series parallel, and dependent reaction. So parallel reaction, for example, A is converting into B, and at the same time A is also converting into C. So this is a parallel reaction. Suppose B is desirable product and C is undesirable product. So with along with a desirable product, some undesirable product is also producing in this reaction, and this reaction is the side reaction, undesired reaction, and this is the desired reaction. So this is the parallel reaction. Sometime A is converting into B and intermediate B, and this intermediate B again converting into C. So this is a series reaction. Sometime there is a series parallel reaction. For example, A is converting into B, A is converting into C, while C is converting into D. So here you can see A, B, C, and D are in series. A is converting into B, B is converting into C, C is converting into D. So A, B, C, D component are in series. But here you can see that A is converting into B, but A is also converting into C. Here you can see. So A, B, C are in parallel. So this is a parallel reaction, this is a series reaction. And these two reaction is called the series parallel reaction. Sometimes there is independent reaction. For example, A is converting into B while C is converting into D. So this is one reaction, this is another reaction. This is called the independent reaction. So because these B is not dependent on C, C is not dependent on B, D is not dependent on A. So these are the independent reaction. So in this lecture we will discuss about the series reaction. The series reaction. So series reaction. So it is a type of reaction in which a reactant form an intermediate product and that intermediate product then converted into the final product. So here you can see general example. A is converting into B. This is the intermediate product and this intermediate product then again converted into C. So here this is one reaction with rate constant K1 and this is another reaction with rate constant K2. So this is A is converting into B. This is one type reaction with rate constant K1 and the B is converting into C with rate constant K2. Now this K is depend on temperature concentration of this product. This K2 is depend on the collision of molecule, the temperature, etc. The general example is this is the this molecule. This is react with ammonia. So here you can see ethylene oxide react with ammonia and it give us the methyl ethanol amine, and that methyl ethanol amine then converted into the diethanol amine, and the diethanol amine again converted into the triethanol amine. So this is the component A, which is converted into B, which is monoethanol amine. It is converted into C, which is diethanol amine, and this diethanol amine is converted into this triethanolamine, so which is D. So this is again a series reaction. So this is a series reaction. Now, uh, okay. So this is a series reaction. Now we will also discuss about there are some terms which you should know about these terms. One is the selectivity and the other is the yield of a reaction. So selectivity and yield of a reaction. Selectivity is nothing but it tells us that how much is one product is important as compared to another product. So how much product is important as compared to another product. This is called the selectivity. And there are three type of selectivity. One is the instantaneous selectivity, which is denoted by S desired product and U is for undesirable product. Selectivity of desired product over undesirable product is equal to the rate of formation of desirable product with respect to the rate of formation of undesirable product. Rate of formation of desired product with respect to rate of formation of undesirable product at any time. It is called the instantaneous selectivity. For batch reactor, we will use this type of selectivity. This is the selectivity of desired product over undesirable product. It is nothing but the number of mole of desirable product formed in the reactor in the batch reactor divided by the number of mole of undesirable product formed in the batch reactor. So this depend on the number of mole. And for the flow reactor, for plug flow reactor or PBR, packed bed reactor or PFR, plug flow reactor, we will use this overall selectivity, which depend on the molar flow rate of desirable product at the exit of reactor divided by the number the molar flow rate of undesirable product at the exit of the reactor. So it depend on the flow. This is the for example, this is component A, the molar flow rate of component A at the inlet condition, and suppose this is the molar flow rate of A at the outlet condition. So it depend on this desired product and undesired product at the exit of this reactor. So this is for the plug flow and bag bed reactor. So here this is about the selectivity. Now we will use another term which is called the yield of a reaction. So yield is nothing but it is the amount of product that is produced when limiting a reactant is fully consumed in a reaction. So when the amount of product that is produced when limiting reactant is fully consumed in a reaction is called the yield of a reaction. So there are theoretical yield, actual yield, etc. And for the reactor, you can use the instantaneous yield, which is nothing but the rate of formation of the rate of desired product divided by the rate of consumption of the key component, which is the limiting reactant, which is can be component A or component B. So the rate of the decomposition of the limiting reactant, the rate of formation of desired product. And for the flow system, you can use the molar flow rate of desired product at the outlet of reactor divided by the molar flow rate of the limiting reactant at the exit of reactor. The key reactant is nothing but it is the limiting reactant or the component A. So similarly for batch reactor, the yield is nothing but it is the mole of desired product produced in the reactor after a certain time divided by the number of mole of the limiting reactant which are converted into the desired product inside the batch reactor. So here you will see this is the you will see now you will see the example. This is the example. The elementary liquid phase reaction. This is example. Here you can see the elementary liquid phase series reaction. So here you will see the liquid phase reaction. Uh, the elementary liquid phase reaction series reaction. A is converting into B, B is converting into C. Is carried out in a batch reactor. The reaction is heated very rapidly to reaction temperature where it is held at this temperature until the time it is quenched by rapidly lowering the temperature. So there is an elementary reaction in which A is converting into B while B is converting into C. When the concentration of B is increased, so at that time we will decrease the temperature of the reactor in order to decrease the concentration of this C. We do not want C because this is undesirable product and this is our desirable product and this is the undesirable product. So once the concentration of B is increased, we will quench, we will decrease the temperature of reactor, and suppose it's a reactor, we will decrease the temperature of the reactor in order to increase the concentration of this B component. So required it show the required information is the plot and analysis the concentration of A, B, and C is a function of time. So we will plot that this is time and this is the concentration of component I. Suppose A component I can be component A, component B, component C. So A will decrease inside the batch reactor, B will increase inside the batch reactor, C will also increase inside the batch reactor. So we will plot and we will analysis the concentration of A, B, and C is a function of time. This is part number one, and part number two is calculate the time to quench the reaction when the concentration of B is maximum. So suppose this is B, when the concentration of B is maximum. So at what time the concentration of B will be maximum? So we will find the time. It can be 3 hours, 4 hours, etc. So we will define the time. And number three, what is the overall selectivity of this batch reactor? Overall selectivity, and what is the overall yield of this batch reactor at this quench time? What will be the selectivity and yield at this three time hours at this time? Suppose at this time or some other time. So once we determine this time, we will determine the selectivity and yield of this batch reactor. And this remember, this reaction is taking place in the batch reactor. And the B is our desired product and C is undesirable product. So the given information is the concentration of A is given to us. It is a concentration of A is 2 molar. Initial concentration of A is 2 molar. The K1 is 0.5 per hour. K2 is 0.2 per hour, and this is the general series reaction. So this is a general series reaction. First of all, write the above reaction in two reaction. So we will write this reaction into, and we will divide this reaction into two reactions. Suppose this is reaction number one with rate constant K1, and this is B is converting into C with rate constant K2. So we will write this reaction into two reaction. Now, so first of all, we will write this reaction into two reactions. This is reaction number one. Here you can see the rate of consumption of component A in the reaction number one is R1A. So 1 shows the reaction number 1 and A shows the component A, reactant A. So it is equal to K1CA. C is the concentration of component A and K is nothing but the rate constant, which is 0.5 per hour. The rate of consumption of component B in the reaction number 2 is minus R2B. The rate of consumption of component B in the reaction number 2 is equal to K2 into CB. CB is the concentration of component B, while K2 is nothing but this value 0.2 per hour. So these are the two reaction. Now there are three components in these two reactions. One is component A, B, and C. Because A is converting into B, B is converting into C. So first of all, we will make component balance on reactant number one. So component A, species A. So we will first of all, there are some steps. So step number one for component A, the step number one is mole balance on component A. You have already know the mole balance in the chapter number one, which is the general mole balance equation is input minus output. Input minus output plus generation is equal to accumulation. So this batch reactor, there is no input, there is no output. Generation is equal to accumulation. So this is the generation. is equal to accumulation. With the passage of time, accumulation is equal to the generation. And you know that the mole per unit volume is nothing but the concentration. So divide this Na divided by V. This V, you will get the concentration of component A, and this is the rate of consumption of component A inside the batch reactor. This is step number one. Mole balance, write mole balance on component A. And step number two, we will write the rate law for these two reactions. And remember that component A is present only in this reaction number one. So the rate of consumption of component A in the reaction number one is equal to K1Ca. So this is the rate law for component A. There is no component A in the reaction number two, so we do not need to write the rate law for reaction number 2 because A is not present in the reaction number 2. This is the step number 2. Now go to the step number 3. Here combine step 1 and 2. So here you can see the concentration of A with the passage of time inside the reactor is equal to Ra, and combine step 1 and 2 mean that this is the Ca divided by T is equal to Ra. Now we know that the component A, consumption of component A inside the reactor is equal to minus R1A, and minus R1A is equal to K1Ca. But here you can see this is plus R1 plus Ra. So here this minus sign will go to this side. It will be equal to minus R1A, minus R1A, and it is nothing but Ra. Ra. So here you can see the minus R1 is equal to this one. So this side, this will minus sign will go to this side, and it will be equal to minus K1Ca. This is the combined step 1 and 2. Now go to the step number 3. So go to step number 3. Here integrate with respect to time. Equation number 1 with respect to time. So here we will integrate this equation number 1. Suppose this is equation number 1. This is equation number 1. We will integrate this equation. dCA by dt is equal to minus K1Ca. So this is separable variable method. dCA will come to this side, and this time will go to this side. Here this. So again dCA by Ca, Ca naught at time t is equal to 0, the concentration of component A will be Ca naught, and at time t is equal to t, the concentration of A will be Ca at time t. So here we know that we will apply the ln rule to both sides. So here this is a function Ca, and this is the differential of function. So it will be equal to ln Ca. And at time t is equal to 0, the concentration of component A is Ca naught, and at time t is equal to t, the concentration of A will be Ca. And this is time 0, and this is time t. So we will again simplify this one, and we will get the concentration of component A, which is Ca at time t is equal to Ca naught e to the power minus K1 t. This K1 is 0.5 per hour, which is given in the question, and this is the time. So this is the time, and this is the concentration. So from this we can plot the concentration with the passage of time. This is the time, and this is the concentration of A. So here we will suppose at time t is equal to 0. Suppose at time t is equal to 0, Ca will be equal to Ca naught, and Ca naught is 2 molar. 2 molar. Suppose 2 molar, and it will then decrease with the passage of time. So the concentration of A will decrease with the passage of time. This exponentially, you can see this exponential function. Now we will go to the component B, and we will apply the same rule for component B. Now species B or component B or reactant number 2, reactant second reactant or the component B. So species B, here you can see species B is present in both reactions A and B. A is converting into B, and B is converting into C. So here this is step number 1. Mole balance on component B is nothing but it is change in the number of mole of B with the passage of time in the batch reactor is equal to the rate of the consumption or formation of component B inside the batch reactor multiplied by the volume of the batch reactor. So mole divided by volume is nothing but the concentration of B, and here this is the rate of component B. Rate law, here you can see R1B is nothing but it is K1CA, and the rate of consumption of component B in the second reaction is equal to minus R2B is equal to K2CB. So here you can check these reaction. So this is the component B. Here you can see component B is A is converting into B. This is K1. B is converting into C, and this is K2 with constant K2. So the rate of formation of component B in reaction number 1 is nothing but reaction number 1. The rate of formation of B in reaction number 1 is equal to K1 CB, C CA, sorry, CA, and the rate of consumption, so minus R2 in reaction number 2, the rate of consumption of component B will be equal to K2 and to CB. So from here you can the rate of formation of component B in this say first and second reaction will be equal to RB. The rate of formation in the both reaction will be equal to R1B plus R2B. So combine these two, it will be equal to K1CA, and this will be go to this side. So it will be equal to minus K2CB. 2CB. So now we will go to this is second number step, and this is the relative rate which we have already discussed. So this is reaction number 1, this is reaction number 2. The rate of consumption of component A in the first reaction is this one, the rate of consumption of component B in the second reaction is this one. So now here you can see the rate of the formation of component B in the reaction number first is equal to minus R1 CA from relative rates. So from relative rates you can see relative rates. Now relative rates you can this is suppose reaction number 1 is converting into B is converting into C. So the relative rate for this reaction will be nothing but a minus R1A divided by the stoichiometric coefficient of this one. So it will be equal to 1 is equal to the rate of formation of component B in the reaction number 1 divided by the stoichiometric coefficient of this reaction. This is for reactant we will use the minus sign, and for product we will use the positive sign. For reaction number 2, rate of this reaction number 2 and this component B, this is one molecule is equal to the reaction number 2 component C divided by the number of moles. So this is 1. So here you can see. And now here these are the relative rates for reaction number 1 and reaction number 2. And we know the information this minus R1A value is given to us, which is nothing but K1CA. K1CA. And this is the minus R2B, which is equal to R2C. And this is R2B value is given to us. So we will put their value. So now net rate of B. So the rate of formation of component B in the both reaction number 1 and 2 is equal to the rate of formation of component B in the reaction number 1, the rate of plus the rate of formation of component B in the reaction number 2. The rate of formation of component B in the reaction number 1 is nothing but it is equal to K1CA, while the rate of decomposition of component B in the reaction number 2 is minus K2CB. Now RB. So now these put these two value in this equation, this step number 5. So here you can see RB is equal to R1B plus R2B. R1B, the value of R1B is K1CA, while the value of R2B is equal to minus K2CB, because this is R2B plus R2B. So this minus will go to this side, so it will be equal to minus R2B, and R2C value is given, which is K2CB. So you can put, and R1B value of R1B is equal to K1CA. So again simplify this one. This will go to this side, and this will be K2CB plus dCB by dt is equal to K1C A. Now solve this equation number x. So solve and integrate. So for the solution of this equation number x, we will multiply both sides of equation x by integration factor. So integration factor by integration factor. So that this type, usually these type of differential equation can be solved by using the integration factor. So integration factor is nothing but suppose the integration factor is this is integration factor, mu of x is equal to integration factor. So multiply both sides of this equation by mu of x. Mu of x, this is mu of x, and this is also mu of x. Multiply both sides this equation by integration factor. So we multiply these both sides by integration factor mu of x, and you can see this is, and the integration factor is nothing but it is e to the power k2 dt. So k2 dt integration factor. So this is, you can see the integration factor is nothing but it is this integration factor. This is integration factor is nothing. Integration factor is nothing but it is e exponential, and this is the integral k2. This k2 is nothing but this one. This k2, this, and this k2 and integration with the passage of this function, this independent variable. Here it is time, so it will be time. So now take the integration of this term, it will be k2t. Integration will be nothing but vector will be equal to e, this is k2, and this will be the time, some constant. So this is suppose integration factor. Integration factor mu of x is equal to k2t. Now so here this is the integration factor k2 e to the power k2t. Here e to the power k2t, e to the power k2t, because this mu of x is nothing but e to the power k2t. This mu of x is nothing but e to the power k2t. This is mu of x. So this is equal to, this mu of x is nothing but e to the power k2t. And here you can see again, this is the, this is the, here you can see the um, product of two function. The derivative of product of two function is, this suppose is the first function, is the second function, and if we take the derivative, so it will be the first function, the derivative of second function, plus second function derivative of the first function. So here you can see this is the first function, the derivative of second function, plus second function into the derivative of first function. So again we will write, and this is e to the power k2t k1ca, which is the left hand side, left hand side. So this is, so these two term will be nothing but the product rule. Product rule. This is the first function and this is the second function. We will take their derivative. So CB and the integration factor, we will take their derivative. If we simplify this term, we will get this the above term, above two terms, these two terms, and this is equal to the left hand side. This is equation number y. Equation number y. Now this is equation number 4. Now this is equation number 4. You can see the Ca, the value of Ca, as we have already obtained. Ca is nothing but it is Ca naught e to the power minus k1t. From the mole balance and from the above steps, we have already determined the Ca. So in place of Ca, we will put the the Ca naught e to the power minus k1t. Okay. C naught e to the power minus k1t, and this e to the power k2t is this term, and this is the c1, and this is the, again the different, the derivative of the two function. Okay, the product rule. Again take the integral of this equation. So take the integral with the passage of time. So we will get this equation. Again, these will cancel with each other, and this k1 c naught e to the power t k2 minus k1 divided by k2 minus k1 plus c naught constant 1 c naught c1. Again, divide this equation by e to the power k2 t this side and e to the power k2 t this side. So simplify this term, we will get Cb is equal to K1 C naught K2 minus K1 e to the power minus K1 t plus C1 e to the power minus K2 t. So this C1 can be obtained. This C1 can be obtained from the initial condition at time t is equal to 0. Cb is equal to Cb naught is equal to 0. So we can get the C1 value from the initial condition. So at time t is equal to 0, suppose at time t is equal to 0, this whole term will be equal to 1. Okay, and this Cb naught will be equal to 0, 0. This will be equal to C1, this will be equal to 1 K1 CNR divided by this one. So from here you can see the C1 value will be equal to minus K1 CNR K2 minus K1. So put this C1 in the equation, and the equation in this equation ZZ, this equation. So in place of C1 we will put this term. So put this term here and take the commons K1 CNR divided by K2 minus K1. This is common, and this will be the e to the power minus k1t minus e to the power minus k2 t. So Cb, the concentration of B with the passage of time will be this one. This is the concentration of B. We will get the concentration of B. Now the concentration of B is obtained. This is the concentration of B. Now take the mole balance on component C, similar as we have already done for component A and component B. The component C mole balance is this one, divided by the NC divided by V, we will get the concentration of C. It is RC. Rate law, the component C is only present in the reaction number 2, so R2C will be equal to K2CB. Step number 3, relative rates. These are the relative rates, and there is the component C is not present in reaction number 1, so it will be equal to 0, and R2C will be equal to RC, and it will be equal to minus R2B from this relative rates, and minus R2B is nothing but R2C. So we will get these. So the concentration of component C with the passage of time will be equal to K2CB. Now put equation number 4 in equation number 5. Equation number 4 is nothing but the concentration of component B, which we have already obtained. So this is K2, this K2, and suppose this is K2, this is K2, here you can see, and this whole term is nothing but it is the Cb, which we have already obtained from the integration factor rules. We have already from this factor. So again, so the concentration of component C will be equal to this one. Again, take the integration of this equation, take the integral on both sides and solve this one. So then we will get these terms. So here you can see this is the constant value. The integral will go inside, minus the integral of the second component with the passage of time, this term. So again this will be equal to Cc, concentration of component C will be equal to this one plus C1. This is constant because after the integration of these components we will get some constant. So I can use the C1. So the C1 can be obtained from the initial condition. At time 0, the concentration of component C will be equal to 0 because at time 0 there will be no B and C in the reactor, in the batch reactor. So C1 will be equal to 1 divided by K1 minus 1 divided by K2. In place of C1 we will put these two value here you can see, and this is the concentration. Again the concentration of C will be equal to this one. And remember this the integration of these two you can obtain from your mathematics, from your integration, you can get these. How these value are obtained? This one. When we take the integration of e to the power minus some constant time with the passage of time, we will get e to the power minus k1 t, and this term divided by this one here. Similarly for this second term. So okay, this can be obtained from the integration rule. You can use integration. Here the concentration of C after simplification, the concentration of component C will be equal to this K1, K2, K1, K2. These will cancel with this K1, K2, and the concentration of component C will be equal to C0 K2 minus K1, and to the K2 minus 1 minus e to the power minus K1t, this bracket close, minus K1 e to the power minus K2t, this bracket close, and this whole bracket close. Okay, this is the concentration. Now the concentration profile is this one. This is the concentration profile. You can see the concentration profile here. This is the time. In part number 1, it was given that plot the concentration profile of component A, B, and C. So the at time t is equal to 0, concentration of component A is 2 molar. C0 was 2 molar. 2 molar. But with the passage of time, the concentration of A is decreasing. Here in the batch reactor, you can see. And with the passage of time, the concentration of B is increasing. Here you can see. Here the concentration of B is maximum. Here, if you see, this is this concentration of B with the passage of time at this position will be equal to 0. This is the maximum position or optimum condition. So here we want maximum B. So we will determine this quenching time. This is the quenching time. It can be 2 hours, 3 hours, depend on the temperature and the reactor type. And this is the concentration of C. And this concentration of B can be obtained from the relation Cb is equal to K1 C0 K2 minus K1, which we have already obtained from the integration factor. And this Ca is can be obtained from C0 e to the power minus K1 t. So the K1 value is given, time can be increasing. 1 hour, 0 hours, you can get the concentration of A inside the reactor. And similarly for concentration of component C. So this concentration of component C, this can be obtained from this relation. Okay. Now this was part number 1. Now at time t is equal to 0, when concentration of B is a maximum, find the maximum concentration of B. So at this point, at optimum condition, the derivative of the component will be 0 because it's a maximum point, maxima. Here you can see the maxima. So at this maximum, we will get the concentration of component B, and we will get the time at this. We can also the time. This is the time. Here you can see from the graph. So here you can see here the derivative will be 0 maxima. So here we can also get the time at this time, the quenching time. So at this time we will start to decrease the temperature of the reactor, and it is nothing but quenching a time. So we will determine the quenching time. So B, the concentration of B, this is already obtained at the at this at the maxima. The concentration of B, the derivative of concentration of component B will be 0 because this was time Ca Cb, and this was concentration of component C. Here the concentration of B is 0. So the derivative of the concentration of component B will be 0 at this time. And this is the concentration of component I. It can be component A, component B, and component C on the y-axis. On the x-axis, it will be time in hours or minutes. So here the derivative of the concentration of component B at the maxima will be 0. Here it will be 0. So this is the concentration. We will take the derivative of this concentration with the passage of time, and we will set it to 0. So here, when after the derivation of this cb, we will get this will be equal to 0, dcb dt will be equal to 0, and it will be equal to this equation, it will be equal to 0. So here you can see this whole term, will be equal to 0, and after rearrangement we will get the time, the maximum time. At this time quenching will start. So it will be equal to 1 divided by k2 minus k1 ln k2 by k1. This k2 and k1 value are given to us. The k1 value is 0.5 and the k2 value is 0.2 in the question, already given in the question. So this k2 is 0.2 and this 0.5 you can see from the question, from the given data. Okay, this k1 value is 0.5, k2 is this one. Put the k1 k2 value in this equation, the maximum time will be 3.04 hours. So after 3 hours the we will start to decrease the temperature of the batch reactor in order to increase the concentration of component B inside the batch reactor, and in order to decrease the concentration of unwanted product, because we have already discussed that we sometimes we want to increase the concentration of one component while at the same time we want to decrease the concentration of another component, mean unwanted product. So this is the ca naught. The ca is equal to this one. Put the value of k1, this k1 0.5, and this is the time. This time is nothing but this maximum time here. This time is the maximum time. This time is the maximum time, 3.054 hours. So put time and k1 value in this equation, and ca naught is given 2 molar. So the ca value at this time, after this time, will be equal to 0.44. The cb value will be equal to 1.09. The cb concentration is given. This we have already obtained from the integration factor rules. So the k1 value, put k1, k2, the maximum time, this time in this equation, the k2, k1 value, we will get the molarity of component B inside the batch reactor after this time. Okay, the concentration of component C will also obtain the C naught 2 molar, K2 and K1 value is given, the time value is given to us, K1 and K2 value are also given. So after 3.05 hour, the molarity of component C will be 0.48 mole per dm cube. Now go to the part number C, calculate the selectivity and yield at this quenching time. What will be the selectivity of the batch reactor and what will be the yield of this batch reactor at this 3.054 hours? It will be the selectivity of component B for the batch reactor. This is the CB concentration of B. This is the nothing but the okay, the concentration or molarity. So here you can see CB value is given to us. It is 1.09, this one. So put this one, and this is the CC 0.48. So 1.05 mole per hour per dm cube per liter, 0.48 per liter. Suppose the volume of reactor is 1 liter, so we will get the mole divided by mole, it will be equal to 2.27. The selectivity of this batch reactor. Yield of the reactor will be the concentration of B with respect to the concentration of A inside the reactor. After certain time, it will be equal to this is the C naught 2 molar, and Ca after the 3.054 hours, the Ca value is 0.44. So put 0.44. This is the Cb, which is equal to 69% or 0.69 will be the yield of the reactor. So this was all about the series reaction in a batch reactor. Thank you very much for your attention. If you have any question about this lecture, you can ask in the comment section. Thank you very much. If you are new to the channel, please like and subscribe. Thank you very much.